Hi folks, I prepared a tutorial or a video clip recently where I had two blocks which were traveling down a track according to certain position pattern as a function of time. One of them was using the sketch-based approach. In other words, the position of the two blocks as a function of time were defined using two sketches. And then the second one was the position of these blocks as a function of time were using the concept of rule, or basically a programming approach to in Catia. I did fuss a lot about using parentheses and braces and things like that when I write a program. However, some of that stuff was not necessary, so I'm going to do a different version of a simplified version of that mechanism. So we have a single block, as you can see here, which is going to be traveling down this track, and the length of the track is around 15 inches, I believe. And the position of the block as a function of time is given by first a uniform velocity, so it goes for 2 seconds at 3 inches per second, and then it stops at that location and then follows a sine curve. Okay, so it does two oscillations with an amplitude 6, up and down, plus and minus, and then after 4 seconds, it does this. After 4 seconds, then again it starts moving to the right at a velocity of 8 inch over 4 seconds, or basically that's 2 inch per second. Okay. Right. Okay, so let's start doing this problem. All right, these are prepared here. Let me go to the assembly design and create the constraints, which automatically are going to be turned into joints later on. So let's anchor the track. There's a track, and then coincidence between this edge and that edge, and coincidence between this face and this face, and update. And since I want this thing to move all the way to the end of the left edge, left side, so this control that edge, and update, and just deactivate or delete this constraint because we don't need it. All right, so its sole purpose was to move the block all the way to the end. Okay, now we're going to go to the digital markup, DMU kinematics, get the magic wand. There's the magic wand. Create your mechanism. Needless to say that there's going to be a single prismatic joint with 1 degree of freedom sitting here. Okay, we then want to write the rule. Well, first of all, let's make this thing a length-driven joint so that we can see whether it's doing what it's supposed to. So the length goes between 0 and the end of the block, which I'll put down as 15 inches. Obviously, mechanism can be simulated, and we can do that manually using simulation with command. If you drag this thing, it moves all the way to the end. Okay, let's put it back. All right. Now we're going to write the formula or the program which emulates this particular position. Notice that these are positions along the track as a function of time, and the expressions for velocities are shown down here because yeah, just to let you know what these are actually, I'm sorry, these are not position. These are not velocities. These are position. This is a mistake here. So these things should not be. This v is to be interpreted as position, not velocity. Right. So let me fix this thing by adding here statement that v is the position, not the velocity. I was not thinking when I prepared this clip. Okay, so how do we create formulas? Formula in a sense of rules. For complicated formulas, you have to do it with rules. So the first thing that you need to do is to go to the Knowledge Advisor, because that's the only place where you can find the icon for the rule. It's actually right here. You can see that right there. You click on it, and you can give it name, and so I'll call this thing oscillating block. This is just a name. You can call it anything you want. Oscillating block. Okay, so here is where we can write our program. So I'm going to say if the time is less than 2 seconds. Look at your graph. You can see that. Look at the graph. If the time is less than 2 seconds, the position is 3 inches over 1 second times t. Okay. So then the position. Now this is the command for the position. So I can write it here. I'll go on the next page, next line. Okay. Equal to. All right. Now what was it? It was 3 inches divided by 1 second times time, variable time. Left side is inches, right side is inches. Okay. Notice that I'm not using any parentheses. In the previous tutorial, I put parentheses here and put these things in braces and things like that, which is not necessary. Else, if the time is less than, now let's see, 4 seconds. 4 seconds. Again, look at your graph. So between 2 and 4, it's doing an oscillation, which is according to this expression. So then if you turn the position is equal to 6 inches, because it reaches 6 inches after 2 seconds to begin with, plus then it does an oscillation with an amplitude of 6 inches. So 6 inches times sine parentheses, another parentheses, time minus 2 seconds. Okay, think about it, makes sense. Times 360 degrees divided by 1 second. Hopefully I didn't forget anything. And let's close this parentheses. There's 2 of them that I have to close. Now, if you wonder where this 360 over 1 second comes from, keep in mind that the oscillation formula is sine omega t. Of course, t is the times, which is the first term, and omega is 2 pi over the period. The period is 2 seconds. The period of oscillation is 1 second. Sorry, if you look at the graph, the period of each of these sines is 1 second. So basically 2 pi over 1 second, or if you convert it to degrees so that the units are consistent, because my default angle I've set it to degrees, so it's going to be 2 pi over 1 second, which means 360 degrees over 1 second. Okay, good. Now the next line. Else, well, else is a uniform velocity. So else is equal to, distance is equal to. Now keep in mind we start at the 6 inch position. You look at your graph. At the end of the oscillation, you start at 6 inch height, and then you go with the velocity, which is let's see now, 8 over a 4 second period. 8 over a 6-second period. This is also a mistake. Okay, over 6-second period, this should be 6. All right. 8 inches this way over 6-second period. Okay, too many mistakes here. That's fine. So it's going to be plus parentheses 8 in over 6 seconds times time. I'm hoping that there are no mistakes. It always pays off to do a little bit of praying here. So let's say okay and see what happens. Obviously, there's a mistake somewhere, so let's find out. It says line 5. Line 5 is down here. I must have, let's see, line 5. 1, 2, 3, 4, 5. Okay, so let's see. This one is okay. The length is equal to 6 inches plus 6 inches times sine of. This is, oh yes, this should be times time minus 4 seconds. That's first of all one mistake. And is that 4 seconds? Yes, that's 4 seconds. Now, hopefully this is the only mistake. Find out. No, still there is a problem somewhere. It looks like the problem is right here. Maybe we have too many parentheses here. 6 inches plus 6 inches times sine of time minus 2 seconds. I think we have too many parentheses here. There's an extra parenthesis here. That doesn't belong there. Right. Excellent. Very good. Okay, so now we're going to test our mechanism. In order to do that, why don't we actually go and create a speed acceleration sensor at this point, and we better recover for displacement. We better recover the same thing that we had in our PowerPoint slide. So speed acceleration sensor right there. So the reference product is the base, and for the point we are taking that point. Okay, and then we do simulation with laws. Over a 10-second period. Okay, activate the sensor, and all we want to do is to plot the position of that location, that point, vertex, as a function of time. And if we did everything correctly, we should be getting the same graph as we had as the input. So here's we want the y position of that vertex, because this is the y-axis. Okay, so let's simulate it. You can see that this is doing the 2 oscillations and then going at the uniform velocity. All right, let's see, graph. Excellent. Now, the one thing is that notice that this doesn't stop at 0, because I should have selected the vertex which is at the end of the block. So let's go ahead and fix this thing actually. Let's go ahead and fix it. So close this, rewind it, close it, and let's go here with this speed acceleration. Let me delete this, create another one. The reference product is the track, and the vertex is that other point. In the first run, I used this point to the right of the end location. All right, let's do another simulation with laws. So activate the sensor. We want the y vertex. So I selected this. That turned into a yes, and then we play the simulation. 10 seconds. This is the 2 oscillations that it was supposed to do. Okay, so now graph it. And notice that it starts at 0, it has at around 14, and it's exactly the same configuration that we have here. There were two mistakes here. I fixed it. There was this V is supposed to be the displacement, not the velocity. And of course, there was a mistake down here. It says 8 inches over 4. It should have been 8 over 6 because it's 8 inches this way, 6 seconds that way. All right, folks. Good luck.